So you've handed in your assignment 6, looks great. How did that huge bonus go? That's what I want to know. You have all the tools. We just didn't talk about it in class. So I'm curious to see how it went. It is December already, and I cannot believe it. So let's do a quick review. Last day we started chapter 7, right? And so, and that's what assignment 7 is on, and also one of the long answers on your final exam. Okay. And so whatever we don't get through, or even whatever we do get through, I'll put up a summary sheet on Moodle, okay? Just so you have all the notes, as well as the notes that we go through here, yeah.
Are there practice finals on the website?
If I haven't posted it already, I will. Yeah, there should be, but lots of practice problems, but maybe not the practice final. The practice final, we'll talk about it next day, but it's just going to be a long list of questions. It's not actually going to be representative of the final, because I get you to do a confidence interval and a hypothesis test for all of them. And so, and on the final, you only have to do one of those, right? But you don't know which one. So giving you practice for everything, right? So it's not indicative of the length, don't worry. But it is the concepts that I'm expecting you to know. Okay? So quick review, we started chapter 7, which is on regression. And we said, okay, well, if we have something like this, scatter plot, we're looking at the relationship between X and Y, between two variables, X and Y. Yeah. And we said, just as a rule, on the y-axis, you're going to have the response variable. And on the x-axis, we're going to have the explanatory variable. You're having a peek at assignment 7, part B. You have to tell me what's the response variable and what's the explanatory variable. What? Is this a trick? You've given me the scatter plot. It's not a trick. It's just that easy. The reason that I make you do it is because it's important to keep track of which is your X and which is your Y later on in our calculations. Okay? And so I give you those, I'm going to call them gimme marks. Right, whatever's on the x-axis, that's your explanatory variable. Whatever's on your y-axis, that's your response variable. And then we talked about describing the relationship. And I think this is where we ended off. I squeezed it in there. Because part A says describe the relationship between length and weight. Okay, so we have to describe this relationship. It's for 3 marks. Just like when we were looking at histograms, we have 3 things that we need to talk about. Okay, in this case, for a scatter plot, describing a scatter plot, we have to talk about the shape or the form. So first thing we talk about is the shape or form, if you prefer. Oops. I like shape because it reminds me of shape, center, spread, right? Kind of on the same track, right? But your options here are either linear or nonlinear. Linear just meaning straight line, right? Can you look at this and just say, okay, well, if you had to describe how these points are moving, would you say approximately in a straight line? Yes, great. Okay. So we're going to be dealing with linear relationships and modeling linear relationships. It's if you have this huge kind of curve, right? Clearly a curve, not a straight line anymore, then you would say nonlinear. Okay. The second thing we have to talk about is the direction. So upbeat. So the direction of the relationship, the direction's either positive, right, going up, 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 or as they're both, as one's increasing, the other one's increasing, right, that's a positive relationship. Or if it's going down, then you have a negative relationship. So it's either positive versus negative. And we said that, okay, a positive relationship is going to look like this, and a negative relationship is going to look like this. Okay. And then finally, we talk about the strength. And I said, well, depending on what, field you're in, there could be 7 layers of strength that you need to be able to kind of keep track of. We're only going to have 2, either it's strong or it's weak. We're not going to look at anything in between. Okay, so either we have a strong relationship, and that's really anything where we can detect some sort of pattern. I would call that strong, or you could throw in moderately strong in there if you prefer, right? But we're just going to talk about strong versus weak. Okay. If you can't see a pattern, right, or if you're kind of struggling to see some sort of pattern, I would call that a weak relationship. Right. I think that's where we ended last day. So let's see here. Let's talk correlation. So correlation, we say things are correlated. We kind of have an idea of what it means for 2 things to be correlated, right? It means that there's some relationship between these 2 variables that we're talking about, right? And so correlation is just a numerical measure of the strength and the direction of a linear relationship. Okay, so it does assume that we have a linear relationship for the correlation that we're talking about. Okay. So correlation is a numerical measure of the strength and direction. Oh, that says direction. Of a linear relationship. So let's pull in a little example. Come on. Hopeless. Anyways, there's gonna be a space there. Line break. So the example that we're gonna look at is, I just stole it from the textbook. So it's the high school graduation rates in all 50 US states and DC, and the percentage of residents who live below the poverty line. And then the definition of the poverty line is income below $23,050 for a family of 4 in 2012. Okay, so anyone who's living below the poverty line, and a percentage of the whole state, of course, and then the percentage of high school grads. Okay? And so just like assignment 7 here, right? I've given you a scatter plot. First thing I'm going to get you to do is to describe this relationship. Okay? And so we're going to look at this and say, well, seems like there's a linear pattern, right? There's nothing that clearly says, oh no, that we have to fit a curve to this. We don't know how to fit curves in this course. You have to keep going in stats to fit curved lines. Okay. But I would describe it as a linear relationship, right? And because they're going down, that's negative, right? Because I would probably say something like this would be my model, right? If I had to just guess, of course, we're going to develop the calculations to find the slope and the intercept of this line, right? But if I had to guess, that's my guess. Okay? And so I have a negative relationship, I have a linear relationship, and because I'm looking at this and I can see some sort of pattern, I'm going to go ahead and say that we have a strong negative linear relationship. Okay. So if I had to describe this, I'd say we have a strong negative linear relationship. We have to touch on all 3 for 3 marks. I'm kind of shoving marks in your face for this assignment. I feel like, here, have 3 marks. Here, have 2 marks. Okay, but you have to touch on all 3 of those. Okay? And if you just want to say all 3, that's fine, or you don't have to make a list or anything like that. Okay, I'll just make a note here. This is my best guess of line of best fit. So I guess I should have snuck that in before the correlation. But anyways, let's talk about, this is important, a scatter plot. Someone made a scatter plot package in R, and of course, I'm going to use it. I'll post the code, but I think it's been a little outdated, so I have to figure out what's going on. Might be another emoji disaster. Anyways, like I said, I'll post this all on Moodle, so we'll just talk about these key properties of correlation. Okay, so correlation, I'll add it up here, I've got some room. Correlation is denoted by lowercase r or capital R. For some reason, the textbook uses capital R, but I'm stuck because almost every other field uses lowercase r. Okay, so I will use r. Okay, the textbook uses capital R. Okay. On your formula sheet, I even have a little note at the very bottom. Note, lowercase r and capital R are used interchangeably. Okay. So it doesn't matter, whichever one you like. Okay. That's the one you can use. Okay. So correlation, remember it describes the direction of the linear relationship, right? So it can be either positive or negative. And so correlation can take on values between -1 and 1. So negative values meaning you have a negative relationship, positive values meaning you have a positive relationship. Okay? And so a correlation of 0, and I'm going to say anything kind of between 0 and 0.5 on either end, right? Positive or negative, we're going to call it weak. Okay? Anything beyond 0.5, right? Either in the negative direction or in the positive direction, I'm going to call it strong. Okay? And so that's what we have here. So we'll call correlations between -0.5 and 0.5. Right? So it's going to end up looking something like this. So if you've got your correlation here, 0 in the middle, -1, +1, roughly between -0.5 and +0.5, I'll call this weak. Out here, I'll call this strong negative relationship. And out here, I'll call it a strong positive relationship. So if your correlation's between -1 and 0, you have a negative relationship. And if it's between 0 and +1, you have a positive relationship. And that's why correlation is just a numerical measure of the direction and the strength of this linear relationship. So let's have a little guessing game. Oops. So which of the following is the best guess, right, we're just guessing, for the correlation between the percentage in poverty and the percentage of high school grads? Okay. So first thing we see is that we have a negative relationship, right? So anything that's positive is out. Okay. So A is positive, D is positive, so that's out. If we're looking at these negative ones, right, first thing that kind of sticks out is that E, -1.5, we can't have that, right? Because correlation only goes between -1 and 1, right? So this one's out. Actually, I should. That just says R is between -1 and 1. Right, so it's out. So really our only options are between negative 0.75 and negative 0.1. So negative 0.1 is really close to 0, right? But because we can look at this and say, okay, well, I actually see some sort of pattern here, we're going to say that it's the negative 0.75, right? Because as soon as we can see some sort of pattern, we're going to say that we have a strong relationship, right? Whereas negative 0.1 is just too weak for us to be able to see some sort of relationship. Okay, so I'll just make a note of that. Since we can see some sort of linear pattern, our correlation would be considered strong. Right. So as soon as you can see some sort of pattern, you have a strong relationship, right? Moderately strong, right? If you're not sure. But like I said, at its core, I'm just going between strong and weak. How about if we just had to look at these? Oh. Another page break. Okay. So which of the following has probably a typo I'll never fix, the strongest correlation? So the correlation coefficient, that's just R, right? So here correlation coefficient is just R or R. Closest to +1 or -1. Okay. And so looking at this here, right, we've got a really strong relationship here, but it's clearly non-linear, right? And so if we tried to fit a straight line here, those dots aren't actually close to the line, right? And so the correlation would actually be pretty low, right? Correlation for this non-linear relationship, right? If you've got a non-linear correlation that you're talking about, right? But that's way more advanced than what we're going to do. Then, yeah, sure, it's strong. But because we have to have a linear relationship, right? This one would be the strongest relationship, just because they're closer together than in D, right? Here they're a little bit more spread out. It's still a strong relationship. And then in C here, right, we've got this kind of vague pattern, right? But we're kind of going from a strong to, I'd say more of a weak relationship here, right? But it looks like a straight line still. Oi, yikes. So because we have this, right, this would actually be a weak correlation. Here we would have the strongest correlation. Here we would have a strong correlation. Here we would have a weak correlation. So one thing to keep in mind, right, is that we have to have a linear relationship for the correlation to apply, right? So we must have a linear relationship for the correlation to apply. Even if we have a linear relationship, correlation does not imply causation. Okay, so correlation does not imply causation. And when I took this course, I think Jason, who was my prof, he spent a whole day just saying correlation does not imply causation. And he would just say it randomly all day or all class. And so correlation does not imply causation. So what do we mean by that? It means that even if we have two things, right, that change together, right? Things like the weather and ice cream sales, right? So those things, right, they're correlated, but we can't say that, okay, well, if we just sell more ice cream, it'll get hot out, right? So that would imply causation, that a change in one causes a change in the other. That's not how it works, right? We just say that, okay, well, they're correlated, so they move together, and that's fine. We're okay with that, right? But as far as causation goes, changing, right, just selling more ice cream, it's like, let's just mark it down and then we'll have good weather for sure, right? It doesn't work that way, right? And so correlation only describes the relationship between two variables and cannot be used to establish causation. Oops. I used to think correlation implied causation. Then I took a stats class. Now I don't. Sounds like the class helped. Well, maybe. So that's correlation. So take home message, right? Correlation, first of all, can only describe a linear relationship. And even if you have a strong correlation, right, we can't use it to say that it causes a change, right? We can only say that, hey, we have this relationship. That's all we know, right? Stats were kind of hands off. Well, all I can say is that there's a relationship there. I don't know what it is. Right. So, any questions about that? Great. So, let's get into 7.2, which is actually called least squares regression. Now, we can call this a regression equation. We can call this a regression model. We can call it a linear model, right? So all these names, so AKA linear model, regression model, regression equation, and I'm sure there's others, right? But all these are referring to the same thing, right? And that's just the line of best fit, right? If you have this relationship that looks like a straight line, what would the line of best fit be? Okay. And so the least squares regression equation is going to be a linear model, right? Just meaning, so linear means a straight line. Model is just something that we can use to model this behavior, right? Without talking about individual elements in there, right? And so all of stats is just modeling behaviors, right? So it's a linear model of the relationship between X and Y. All that is to say, line of best fit. And I remember, I feel like it was like high school chemistry where we had to fit the line of best fit, but we just ended up taking our rulers and just looking, just kind of eyeballing it. We were like, oh yeah, here it is, great. That's not how it works. Okay, so we're gonna develop the formulas for finding the slope and finding the intercept. Okay, and yeah, maybe you guys had proper line of best fit educations. No? Well, here you go. Here it comes. Any straight line, you might remember something like y equals mx plus b, right? Oh yeah. And if you're like me, you're probably thinking, yeah, sounds familiar, but I cannot remember what it is. That's okay, right? It's the equation of a straight line. So just y equals mx plus b. That's just the equation of a straight line. So anything that you can rearrange into this form, right? Y equals, and then something attached to the x and then something on its own, that's a straight line. Okay. So where m is the slope and b is the intercept. I'll just call it the intercept. It's actually the y-intercept. Of course, there's an x-intercept, so where the line crosses the x-axis. We're not going to be interested in that. We're always just going to talk about the y-intercept. Or in our case, on our formula sheet, I give you the least squares regression line, but I tell you that it's going to take the shape of y hat, another hat, but different context. So it means something different, just to confuse you a little bit. Okay. A hat in regression means a predicted value. Okay, so I'll jot that down in a second here, but we have y hat is b sub 0 plus b sub 1 times x. But if you squint, you can probably convince yourself that this has the same form as y equals mx plus b. Right. We've just got this slightly more grown-up notation, b sub 0, b sub 1. Guess what? Population estimates or population parameters are betas, right? We're not going to get there, but that's why we use b's, because they're related to the betas. But yeah, it's a little itty bitty 0. It's worth nothing. because it's 0. So now because b sub 0 is on its own, right, this is your intercept. And because b sub 1 is attached to the x, right, this is your slope. But if you have a look at your formula sheet, right, I say that here's your least squares regression line, right, just so you have it. And then I say with slope b sub 1, so I tell you that b sub 1 is a slope, and then I tell you how to calculate it. And y-intercept b sub 0, so I tell you that that's the intercept, right? And so I always kind of joke and say that if I gave you guys the opportunity to make like a cheat sheet, right, limited space, you had to write a little cheat sheet that you were allowed to bring in. This is not the case, but if I did, and then I said, okay, now bring out that cheat sheet, and then cross off everything that's on your formula sheet, you'd have nothing left on your cheat sheet. I guarantee it. It's all here, okay? Or at least very little, and by the time you write it on cheat sheet, you'll have memorized it anyways. It's actually kind of a good study trick. Just try to condense everything. By the time you've condensed it all, you definitely won't need to use it. It's all up here. Okay. So you can use that little study trick. Okay. But everything's on your formula sheet, right? You just need to know how to navigate it. Okay. And so we've got a slope, we've got an intercept, and we'll also make a note that y hat is the predicted value of y. That says predicted. The reason we've got a y hat is because the whole point of fitting a line of best fit or a regression equation is to be able to predict future values, right? And so the goal of regression is to predict rewrite that, is to predict values of y. Y, remember, is the response variable, right? Which is the variable that you're interested in your studies. And so, yeah, you've collected this data, right? And then you want to use it to develop this model so that you can say, okay, well, this is how the length of a marmot is related to their weight, right? And then you'll be able to predict the length. Let's say it was something more expensive to measure, right? I can't think of anything relating to marmots, right? But if you've got something that's really expensive to measure, right, and you have something cheap that you think might be able to help you predict what that expensive thing is, right? You'd want to build this model and say, okay, well, if I know how to measure this cheap thing, no examples come to mind, then I can use that to predict the more expensive thing to measure, right? And so predictions, that's what it's all about, okay? And so we want to predict values of y, okay? And to do that, we're going to calculate the slope, right, with that equation I've given you, and we're going to calculate the intercept, and then we'll be able to put in any value of x that we want, and then calculate the predicted value of y, right? And so we will find the slope and intercept, then plug in any value of x to predict y. So I'm actually gonna skip that. First, we're gonna talk about, so before we do any calculations, I want to define the definition of the slope and the definition of the intercept. Okay, because if you look at your assignment, okay, part D, I ask you to find the slope, so just calculate it. And part E, interpret the slope. So to interpret the slope, you have to take the definition of the slope and apply it to this problem in general. Okay? And same thing for G, interpret the intercept. Is it meaningful? Same thing, you're going to apply the definition of the intercept to this particular problem. All right, so first let's develop these definitions and go from there. So the slope says that for each unit increase in x, we will see a slope increase. We will see a slope increase in the predicted value of y. So we'll just leave it there for just a little bit. We'll define the intercept. So the intercept is, if we look here, right? So the slope, if we increase x by 1, then we'll see a slope increase in the predicted value of y. For the intercept is the predicted value of y when x is 0, right? So it's where it crosses the y-axis, right? But by definition, it's the predicted value. The predicted value of y when x is 0. I'll always ask you if it's meaningful. Okay, so I'll always ask you, is it meaningful? Okay. What I mean by that is, okay, well, if you know that the predicted value of y is 4 when x is 0, right? You have to ask yourself, well, can x be 0? Right? So in this case, right, we've got the weights. Do you even care what the predicted value of the length is when the weight is 0? Probably not. A marmot that weighs 0 doesn't exist, right? And so in this case, right, it's not meaningful because a marmot that weighs 0 doesn't exist, right? And so even though you will have a predicted value of y, right, you'll have a predicted length, it's not necessarily meaningful in all cases. And so you have to argue whether x can be 0 or if it will never happen. So here's the thing. For these regression equations, if you're looking at the formulas, so to find the slope, you need the correlation, you need the standard deviation of the y's, right? So you've got S sub y and S sub x. So you need the standard deviation of the y's and the x's. And then moving on to the intercept, you also need the sample mean of the y's and the sample mean of the x's. Okay? And so I need to give you 5 pieces of information in order for you to go ahead and do this type of problem. Okay? So we will need 5 pieces of information to construct a least squares regression line, or to construct a regression equation. Sometimes I get lazy. Still a regression equation. And so you have to be flexible when you're reading these things because they all mean the same thing, right? Regression equation, linear model. So we need to know X bar. You need to know Y bar. Right? The sample mean of the X's, the sample mean of the Y's. You need to know the standard deviation of the X's and the standard deviation of the Y's. Okay? And this is why it's so important, right, that I even give you 2 marks for it, that you identify the response and the explanatory variable, right, because Y is your response variable and X is your explanatory variable. And I also need to give you R, the correlation. There's 2 ways that a question like this can go. I either give you all these 5 pieces of information, okay, and then at the end, I ask you, what percentage of variability in Y is explained by the least squares regression line on X? That sounds really wordy, right? But as soon as you read percentage of variability, you're going to think R squared. Okay, so I'm going to take a little detour before we actually get to these calculations. And that's just because I want you to have all the tools that you need to do the assignment, of course. Okay, so R squared, by definition, and you've already pulled up the R squared in the lab, right? We found the R squared with the summary of the model command. Okay, so R squared is the percentage of variability in Y explained by the least squares regression line on X. That's really wordy, right? But as soon as you see percentage of variability, you can basically stop reading. Okay? So as long as you recognize, okay, percentage of variability in Y explained by the least squares regression line on X, okay, fine. But R squared is just the correlation squared. So if you have the correlation, you can find the R squared. All right, so this is just the correlation squared. Okay. The reason I bring this up right away is because part C, which we kind of glossed over, right? I tell you that 65.11% of the variation, so percentage of the variation, percentage of variability, okay, So R squared is 65.11%, or we need to work with the decimal, of course. Okay, so on assignment, I'm telling you that R squared is 0.6511. Right? And then I ask you to find the correlation between the length and the weight. Right? So even though I haven't given you, I've given you the means and the standard deviations of both the response and explanatory variable, right there in the blurb. Okay. But I haven't given you the correlation yet. Okay. So first option is I just give you all 5 things that you need, including the correlation. And then at the end, I ask you, what is the percentage of variability? Blah, 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 blah. Then you have to calculate R squared. Or I can give you R squared and ask you to find the correlation. Okay. So let's do an example. Use the percentage of high school grads example. Say 70% of the variability in percentage in poverty, right, that's your Y, is explained by the least squares regression line on percentage of high school grads. Percentage of high school grads, that's your X. If I ask you to find the correlation, so just giving you an example that you can use for the assignment. So then I'm saying that R squared must be 0.70. Right? And this is the correlation squared. Right? If I have to find the correlation, can't I just take the square root of both sides? Right? So if I take the square root of 0.70 is the square root of the correlation squared, they're going to cancel. Where's my trusty calculator? I don't think I have it. Man, oh man, I didn't bring it. What's the square root of 0.7? I give up. That's good. Thanks. Close enough? 0.8366. Okay. Is the correlation. One thing with squaring values is that squaring values just always make everything positive, right? If you square a negative number, it becomes a positive number, right? So we lose the positive or negative. All right, so one thing that we have to do is check the direction of the relationship. To make correlation negative, if the relationship is negative. relationship is negative. So I'll scroll up here. It was a while ago, I guess. We had this. Okay. So here, right, we can glance back at our scatter plot and just say, okay, well, because we have a negative relationship, right, we know the numerical value of the correlation, but we also need to add the negative, right? So you would say something like, since we have a negative relationship, the correlation, which is R, is negative 0.8366. So that's how you would find your correlation, right? And that's how you're going to find your correlation on the assignment. Or if I just give you the correlation to begin with, the last question would be, what is the percentage of variability in Y explained by the least squares regression line on X?
And then if it was a positive relationship, then it would be
just positive. Yeah. Good. Okay. Oh yeah, but because, so here you have to look at the relationship on the scatter plot. So on the assignment, right, you're okay because you have a positive relationship. But if your scatter plot showed a negative relationship, then you would have to tack on that negative. Yeah. Because it's just that it gets lost in the squaring of things. Okay. All right. Let's get these actual values. Or we're given the correlation like this. So you need a scatter plot. First thing I would do is get you to describe this relationship, which we already did. All right, we have a strong negative linear relationship. Great. The response variable is the percentage in poverty, and the percentage of high school grads is the explanatory variable. Right. And so we've just organized this information just so we can keep track of, okay, so the mean of the percentage of high school grads is 86.01. The standard deviation of the x's is 3.73. The mean of the percentage in poverty is 11.35, and the standard deviation of the percentage in poverty is 3.1. And then the correlation is just negative 0.75. Yeah, close enough. I just made the other number up, right? So, pretty proud of myself. All right, so if we have these 5 things, right, regardless of how we got the correlation, right, whether it's given to us or we have to calculate it, right, now we can find the intercept. Or sorry, we start with the slope. Don't worry. I make you do it in order in the questions. Why do we have to find the slope first? Because we actually use the slope to find the intercept. Right? Of course, on the final, if you find the wrong slope, but you follow through and do it correctly later on, then that's fine. You won't lose any marks. Just for the slope calculation, of course, can't give you full marks. Okay, but I do follow through and make sure that you kind of did it right, that idea was there. Okay. So find the slope. the slope on our formula sheet is B sub 1 is the correlation times the standard deviation of the y's over the standard deviation of the x's. And you don't want to twist those around because it'll fuck everything up. Right? So our correlation is negative 0.75. The standard deviation of the y's is 3.1 over the standard deviation of the x's, which is 3.73. Now, hopefully you don't mind, I've got these Martha Stewarted because I managed to forget my calculator. Negative 0.623324,397. Interpret the slope. Each unit increase in x, right? So remember, we're just applying the definition of the slope to this particular problem. Here, our x is the percentage of high school grads. So each unit increase in the percentage of high school grads I'll say for each unit increase. For each unit increase in the percentage of high school grads, we will see a negative 0.623 increase. Okay. Even though it doesn't sound that great, I apply the same definition to positive or negative slopes. So a negative increase, that's a decrease, right? But then, so, or 0.623 decrease. The tricky part is I don't want to see a negative 0.623 decrease. So that's an increase, right? So you have to be careful. So I just stick with the slope amount increase, regardless of whether it's positive or negative, because that's the only way that I can make sure that I'm actually saying something true, right? So we will see a negative 0.623 increase in the predicted percent in poverty, right? Because the slope in general was for each unit increase in x, we will see a slope increase in the predicted value of y. Right? So we just apply the definition of the slope to this problem. Okay. Find the intercept. So the intercept on your formula sheet is b sub 0 equals y bar minus b sub 1 times x bar. So you have to use that slope from before. So we have 11.35. I'll just give you those numbers. Right, so the mean of the y's was 11.35 and the mean of the x's was 86.01. So 11.35 minus negative 0.623324397 times 86.01. You have to multiply out that first chunk before you can subtract it from 11.35. Otherwise, you're doing illegal math, right? So we have to do 11.35 minus negative 53.61213137, which is going to be 64.96213137. It'll be given to you because it's the mean of the response variable. Right, so on the assignment, it's given to you in the blurb. Here, I gave it to you as a table. Because you need the mean of X and Y, and you need the standard deviation of X and Y, and the correlation. Okay. So finding the intercept, calculations aren't that bad, right? But what if we have to interpret the intercept? Is it meaningful? The intercept, right, is the predicted value of Y when X is 0. Okay. So we're going to say the predicted percent in poverty when percentage of high school grads is 0 is 64.96%. Is this meaningful? Are we ever going to have a state with a 0% grad rate, high school grad rate? Probably not, hopefully not, right? Unless they move to some sort of other educational system, but then this doesn't apply anyways, right, as a metric. So since there will never be a state, bless you, with a 0% grad rate, the intercept is not meaningful. Then I'm going to ask you to construct the regression equation. In general, right, you have y hat is b sub 0 plus b sub 1 x. So in our case, we have y hat is 64.96. Let's go to 3 decimal places, maybe 962 plus, but it's negative. Yeah, plus negative, what was it? 0.623 times x, right? Or if we want to just write it with the negative 64.962, oops, minus 0.623 x. Okay. If a state, bless you, has an 80% high school grad rate, what is the predicted percentage in poverty? So now you have to use this regression equation to predict future values of y, right? So you've got this state with an 80% high school grad rate. Okay. Tricky because we're using just the percentages as the numbers, but you're going to use the y hat is 64.962 minus 0.623 times 80. Oh, good. Forgot I had to follow these numbers. 64.962 minus 49.6. I rounded too early on here, but same idea. One of you will have it. So then the predicted percent in poverty is 15.36%. One little itty bitty thing, right? If you're predicting for values outside the range of the data, right? So in this case, our data, so our X's went from somewhere between 75 to, let's say, 100, right? If you're using a value of X to predict Y that's outside this range, you're extrapolating, okay? And so you can still use it, but you're not as sure of your predictions. Okay. When predicting with values of X beyond the range of your data, you are extrapolating and your prediction is not as reliable. Oops, it says reliable. Now you can do all of assignment 7, and it's due on Wednesday. But we basically went through it together now, so should be okay. See you on Wednesday for our review day.